We're going to go ahead and take a look at exponential functions. An exponential function is where your variable x is in the exponent. The number that your exponent is on, b, is what we refer to it, has to be positive and can't be 1. So something between 0 and 1 or something larger than 1 is what it has to be. And then a, what's in front, can be any number you want. So let's consider y equals 2 to the x. We're going to go ahead and graph this. So I'm going to choose some different values of x to put them in. And now we'll go ahead and plug this in. 3, so 2 cubed, you know, is 8. Put in 2, 2 squared, you know, is 4. Sorry about that. Plug in 1. I get 2 to the first. Plug in 0, and you should remember anything to the 0 power is 1. Plug in negative 1, it'd be 2 to the negative 1, which really means 1 over 2. Plug in negative 2, it'd be 2 over 2 squared, or 1/4. And then we can plug in our 1/8, or plug in negative 3 to get out 1/8. If we go ahead and plot those points on our graph, we would get this shape here. Now, let's go ahead and look at y is equal to negative 1/2. We'll use the same values of x. Plug in negative 3. The negative flips our fraction upside down, so it'd be a 2 cubed. Plug in our negative 2. The negative flips it upside down, so it'd be a 2 squared. Plug in 1. Negative 1 flips it upside down, and then we got to raise it to the first power, which is 1. Plug in 0, which you should remember is 1. Plug in 1, doesn't change it, so it's 1/2. Plug in 2, it's going to be 1/2 squared, and then plug in 3. When you plot these points, you will get this. Now notice, this one goes up as you go to the right, so we consider that to be a growth. This one goes down as you go to the right, so we consider that to be a decay. They both level out at the x-axis, which is y equals 0. But they still go on forever, left and right, forever. So exponential growth, what your exponent's on, b, has to be greater than 1. Exponential decay, what your variable's on, b, has to be between 0 and 1. So consider our exponential function. If we plug in x being 0, we get a times b to the 0, but b to the 0 is 1, 1 times a is a. So therefore, our y-intercept is also a, because your y-intercept is what you get when you plug in 0. Do we have an x-intercept? These two graphs back here that we were looking at never touch the x-axis. Do they get extremely close to it? Yes, but never, never touch. So we do not have any x-intercepts. But because they continue to get closer and closer to the x-axis, our y equals 0 would be our horizontal asymptote. Here we need to solve this for x, but here we have our variable in the exponent. So this is referred to as an exponential equation. Well, on the left we have 6 to a power, the right we have 6 to a power. Since we have the same base on each side, we could just set the exponents equal to each other. And then all we'd have to do is solve it. So we could add an x to both sides, subtract a 1 from both sides, and divide by 3, and we get x to be 2. But looking at this one, we don't have the same base on each side. Here we have a 27, here we have a 9. But is there a way we could get the same base on each side? So is there another way you could think of 9? And is there another way you could think of 27? Now, I know sometimes people are tempted to say, I'll just multiply this side of an equation by 3. But remember, what you do to one side of an equation, you have to do to the other side also. So you can't just multiply one side by 3. But you could think of 27 as a 3 cubed, still with that exponent. And you could think of 9 as being a 3 squared, still with that exponent. So now we'd have an exponent raised to an exponent, so you multiply those exponents. Exponent raised to an exponent, so you multiply those exponents. But we'd end up with 3 to the power equaling 3 to the power, so we should be able to let those exponents be equal to. Here we'd have 3 times this, and we'd have 3 or 2 times this here, so we get 3 to the power equals 3 to the power. Set the exponents equal to each other, solve it, subtract an x from both sides, add a 6 to both sides, we get x to be 3. So if it's not the same base on each side, you need to get the same base. If it is the same base on each side, just set the exponents equal. If it's not the same base on each side, try to rewrite your base as something to a power and the same base on the other side to the power. So a quick review. If you had your basic y equals x squared, which you know is a parabola, and I came along and said, how does this graph differ? You should remember that that is 3 to the right. So it's a horizontal translation of 3 to the right. If I put the minus 3 after the squaring, you should remember that that is just 3 units down. That type of stuff also works for exponential functions. And we'll look at that on the next page. But we're going to start out with our basic function like this. And then we'll be going ahead and comparing it to this. So once again, I'll go ahead and use negative 3 to 3. Do you have to use those? No, but they're just nice numbers to work with. Plug in negative 3, plug in negative 2, plug in negative 1. So you could either do it by hand or you could plug this into your y equals. Then remember you can go second window, hit table set, started at negative 3, and then look at second graph, which is your table, and it will give you these values. Plotting these points, you would get this shape right here. Now, my question for you is, if this is your basic graph, how does this x minus 3 as an exponent affect your graph? Well, you should realize that that minus 3, which is hanging out by your x, is going to then just move it 3 units to the right. So all we have to do is take this graph, slide it 3 units over, and we get this graph here. So how does this graph here differ compared to our original? And well, you should realize that if we have a minus 3 after the whole thing, it just takes our original graph right here and just drops everything down 3 units. And so you would get this. So once you know your basic graph, you can easily do your translations like this, just like what we were doing with normal functions before. Quick side note, when you're dealing with our first one over here, which we knew was a horizontal translation, there's a second way you could have got to it. It's actually a vertical stretch. Now this only works with exponential functions. Your x minus 3 you could think of as x plus a negative 3. Then you should remember when you add exponents, that's when you multiply the bases. And then this right here is a negative exponent on it, flips it upside down. You cube the top, cube the bottom, you get this. So if you did a vertical stretch to your original, you would also get this right here. But that's a side note. Your main thing is realize that you could take your original and just move it 3 to the right. So here we want to find an exponential function. We're told our y-intercept, and we know it goes through this point here. Your y-intercept is really a point also. You're not left and right any, but you're up 6. So if we wanted, we could take our x being 0 and our 6 being our y and plug it in. Well, remember, b to the 0 is 1, so we get a to be 6. So if we rewrite this plugging in 6 for our a value, we would get this. Now we've not done anything with this point yet, so all we can have to do is really plug in that x and plug in that y. Plug in our x being 2, set it equal to our 3 over 32. Now we can divide both sides by 6 to solve it for b. We get 1 over 64 is equal to b squared. Then we can solve it for b by taking the square root of both sides, and we get plus or minus 1/8. However, remember according to our definition that this value of b has to be positive and not equal to 1. So that means in the context of our problem, the b being negative doesn't work. So it's only going to be 1/8. So we'll rewrite this. We'll go f of x equals, plug in our value of a, which we knew was 6, plug in our value of b, which we just figured out to be 1/8. Well, we'll do the same thing here. We will find a function, but here we have a, b, and c, where c is your horizontal asymptote. If our horizontal asymptote is y is equal to 72, we know that c is your horizontal asymptote of 72. Now, we have our y-intercept. Remember, that's when x is 0, we get out this. So that's a point. So once we plugged in our c, we could now plug in our point with x being 0 and setting it equal to 425. Remember, b to the 0 is 1. 1 times a doesn't change it. Now we can go ahead and get a by itself by subtracting 72. So now I'm going to take a, substitute it in here, and I get this. We've not done anything with this other point. So all we have to do is take this point, which is an x being 1 and a y being 248.5, and plug it in. Remember, b to the 1 is still just b, so I'll just subtract 72 from both sides, divide by 353, and I get b to be 1/2. So now I'll make sure I rewrite my original just with a, b, and c all plugged in. Once again, a was 353. We just figured out b to be 1/2, and c was your y, your horizontal asymptote of y is equal to 72. Now, exponential functions are useful when it comes to looking at growth and decay. A lot of times if you put money in a bank, you're able to earn interest on it and have that money grow. The formula that works for that is this a is equal to p times 1 plus r over n raised to the nt. P is your initial amount you put in, referred to as your principal. R is your interest rate, but you need to change it to a decimal instead of a percentage. N is the number of times it's compounded per year. So if it was compounded quarterly, that would mean 4 times a year. T is typically your time in years. And A is the amount that you get out after all that time. So consider we have this problem. We're investing $1,000 at an interest rate of 7%. It's compounded monthly. What's our amount after 20 years? What you're putting in initially is $1,000. That's your P. Your interest rate is 7%. You got to change that to a decimal, move your decimal point over 2 spots. Your time is 20 years, so T is 20. It's compounded monthly, which means it's 12 times a year. All we have to do is take these values, plug them into our formula, replace P with 1,000, parentheses 1 plus our interest rate as a decimal, divided by n, close our parenthesis, raise it to the n times t. A is already in one side by itself. All we have to do is just type it into our calculator. And we end up getting $4,038.73.